In this lecture, we are going to study the magnetic materials. The first type of magnetic materials we are talking about is paramagnetic materials, which have permanent magnetic moments in atoms. In a paramagnetic material, a weak magnetism results from these permanent magnetic moments, which interact weakly with one another. The permanent magnetic dipoles are randomly oriented in the absence of an external magnetic field. By applying an external magnetic field, the dipole moments in the materials tend to line up with the field. For example, when we place a paramagnetic material in an external field B0, as discussed earlier, the dipoles experience a net torque, tend to align dipoles with the external field B0, which produces a net magnetization M. Please note that M is parallel to B0, therefore it would enhance B0. The total magnetic field B should be the vector sum of these two fields, where Bm is a field due to the magnetization of the permanent dipoles, which is equal to mu0 M. Now let's examine the difference between the behaviors in a paramagnetic material and a dielectric material when applying the external field. In both cases, the torque of the dipoles causes the alignment of the dipole vector parallel to the external field. However, in the paramagnetic material, the alignment increases the external magnetic field, while the effect of the dielectrics is to reduce the external electric field. It's found that the magnetization M is linear proportional to the external field B0. The relation between M and B0 is expressed by this one, where chi M is called the magnetic susceptibility, which is a dimensionless quantity. The magnetic field B is rewritten as this one by substituting M. Here, kappa M is called the relative permeability of the material. For the paramagnetic materials, chi M is larger than 0 and kappa M is larger than 1. The magnetic permeability of a material could be defined as this one. Mu M equals kappa M times mu0. Obviously, the magnetic permeability of a paramagnetic material, mu M, is larger than that of free space, mu0. The second type of magnetic materials is diamagnetic materials. For a diamagnetic material, there are no permanent magnetic dipoles. But when an external magnetic field is applied, a weak magnetic moment is induced. But the induced moment is in the direction opposite the external field. Thus, the magnetization M and the induced Bm are antiparallel to the external field B0, causing the reduction of the field. This effect is similar to that of a dielectric material, which reduces the external electric field. In a diamagnetic material, kappa M is smaller than 1, so the magnetic permeability, mu M, is smaller than that of free space, mu0. Please note that diamagnetism is present in all materials, but the effect is much smaller than those of paramagnetism or ferromagnetism. It's evident when other effects don't exist. Here we have an example showing diamagnetism. A superconductor exhibits diamagnetism in the superconducting state. We have zero or little field within the material because external field lines are excluded from the superconductor. This phenomenon is known as the Meissner effect. Please look at this figure. A small permanent magnet levitated above a cooled superconductor disk due to this effect. Now let's talk about ferromagnetic materials. Compared to the paramagnetic and diamagnetic materials, ferromagnetic materials exhibit strong magnetic effects produced by a strong interaction between neighboring atomic dipole moments. The typical examples of ferromagnetic materials are iron, cobalt, nickel, and so on. The strong interaction between the atomic magnetic moments produces a much stronger alignment than that in paramagnetic materials. Once the moments are allied, the materials remain magnetized even though the external field is removed. Let's explore the magnetic effects of ferromagnetic materials in details. As shown in the figure, all ferromagnetic materials consist of microscopic regions called domains. In the regions of the domain, all magnetic moments are allied. Please look at this figure. When the sample is placed in the external magnetic field B0, the size of those domains grows with the field, and the magnetic dipoles line up parallel to the external field. When the external field is removed, the sample will remain a net magnetization in the direction of the original field. Therefore, the field is enhanced dramatically due to ferromagnetism. The total magnetic field inside a ferromagnet is 10 to the power of 3 or 4 times greater than the applied field. The permeability kappa m of a ferromagnetic material is not a constant. The total field B, or the magnetization M, doesn't increase linearly with B0. The relationship between B and B0 is dependent on the previous history of the material. The phenomenon is known as hysteresis. This figure shows us the magnetization M as a function of the external field B0. The loop ABCDEF is called hysteresis curve. In ferromagnetic materials, the strong interaction between dipole moments can keep them allied, even when the external magnetic field is 0, as shown in the figure. Thus, a strong magnetic field is produced by these allied dipoles without the existence of external field. This is the origin of permanent magnets. At ordinary temperatures, the alignment of the dipole moments could not be interrupted by the thermal agitation. However, when the temperature reaches or goes above a critical temperature called Curie temperature, the ferromagnetic material will lose its residual magnetization. Above the Curie temperature, the thermal agitation is strong enough, leading to a random orientation of the moments. As a result, the ferromagnetic material becomes paramagnetic. Up to now, we have talked a lot about the magnetism. From the next lecture, we'll move to a new topic, electromagnetic induction.